Hello, my name is Dr. Alec Megabo from New York University. I've been asked to talk on the topic, what have we learned and accomplished by participating in the ACR Dose Index Registry. Next slide. My financial disclosure, I am a consultant for Bracco Diagnostics. Next slide. I'd like to acknowledge help from people at ACR, Laura Coombs, Maithri Chatfield, Penny Butler, for some feedback on this talk, and at NYU for Emilio Vega, who really took the ball and did a lot of the work that I will describe to you to allow us to participate. Next slide. So why is there a dose index registry? The question was asked, what would be the national average level of radiation administered by imaging facilities for a particular examination, for example, CT of the head? And actually in 2003, as late as 2003, there was no answer to this question. Next slide. So it was conceived to create a dose index registry which would provide accurate and objective measures of practice processes and outcomes to allow the facilities to compare their dose indices to peer facilities and national averages, and finally to hopefully develop a range of appropriate dose indices for a variety of CT examinations. Next slide. It was a simple idea, but a very complex implementation. It was first proposed in 2004 by two members of the American Association of Physicists in Medicine, Dr. Richard Morin and Dr. Donald Fry. Dr. Morin will be giving a talk on the dose index registry at another time during this symposium. CT, since it was clearly the most significant in terms of global radiation exposure, was chosen as the first application. So in 2005, over 12,000 DICOM headers were collected from Mayo Jacksonville, and that formed the first database for the registry. The first external contributions already in 2006. The national database was piloted in 2007, so we're already 3 years from the into the implementation. Siemens was chosen as a single vendor for the pilot. They modified DICOM headers, and ACR developed software to transmit these DICOM images from a freestanding PC. All of the above was accomplished by December 2008. So from concept to launch was 4 years, a very complex process. Now, in the initial phase, all of the sites had to sign a business agreement with the ACR. We worked with Siemens. They provided a dedicated PC. We installed the ACR software at our site and implemented a manual workflow path to get the DICOM image to the dedicated PC. In that original pilot group, which was actually configured in 2009, Mayo Jacksonville, Mayo Rochester, University of Colorado, UCLA, NYU, and the University of Iowa were the participants, and I'm proud to have been part of that initial implementation. And these results were presented at the 2009 RSNA, 5 years after this was thought about. Next slide. In the second phase, which is ongoing, a seamless method of transmission from CT from any vendor was established, and beginning to create an integrated healthcare enterprise radiation exposure monitoring system at a national level was undertaken. Next slide. In order to find out about the dose index registry, if you go to the web and log in, this is into the ACR site. This is the homepage for a variety of dose registries. The one that we're talking about is the dose index registry, the DIR. If you go there, you will come to the homepage of the dose index registry. The website is at nrdr.acr.org. This is the one that we are interested in. As of 2012, you can see how many sites, particularly in the Northeast, are participating in this. particular project, with more sites expected to come on board in the near future. So from 6 sites now to quite a number of sites is really remarkable progress over a relatively short period of time since the national launch. Next slide. Now in this slide, I just illustrate the complexity of the DICOM report. This is one of several pages of a DICOM report from our facility, but the vendor, manufacturer, and embedded in here is information about the way the scan was performed and the dose indices that were used. This material is actually transmitted from the scanner to the Triad site server. This is where the ACR software exists, which takes those streams of numbers and anonymizes them and converts them into the database such that they can be housed there, and then the sites will get their feedback reports. The ACR was instrumental in developing this Triad software and also in transforming this DICOM data into a usable report. Next slide. There are some challenges in going nationally. I remember participating in several conference calls to try to decide which dose index would give the best assessment to each facility. For instance, if just CT-DI vol was reported, if a certain protocol had a monitoring scan, this would artificially raise it. DLPs as the single dose index are difficult to compare because of the variation in patient sizes. So what was thought is that they would report both CT-DI and DLP. In terms of the examination naming, this was extremely challenging because there's a wide variance in protocols for the same exam name across multiple institutions. What NYU does for a CT hematuria may be totally different than what Mayo Clinic does, yet they would, to the dose index registry, have exactly the same name. And also there are technical variations between the individual scanners within each department. So for instance, some of our scanners have denoising capabilities, other scanners do not have denoising capabilities. Different detector configurations will result in different dose indices, and when all of these are lumped together, you can either artificially raise or lower your practice because you get a conglomerate report. Next slide. One of the ways to try to normalize the naming of exam was to create what's called a Radlex Playbook identification. This allows each facility to map study descriptions to standard terminology. The mapping is based on the body region, the contrast enhancement, yes or no, anatomic focus, whether it's a CT angiography, whether it's a pediatric case or an adult case. This is really the critical step in accurate assessment of the dose indices that the facilities are using. If you go to the website, there's a fairly complex tool. This is from NYU. That's our facility number. We've mapped over 500 different protocols at our institution. We haven't mapped several other ones, but this would be the way that you would map and try to match what you're doing closest to some of these protocol variants from the ACR, and then this can be translated into a common name so that you would get a more accurate comparison with peer and local institutions. Next slide. The entering into this Radlex Playbook requires a high skill level of the technologists to accurately complete and do the mapping. As you can see on this little chart here, these are all the different protocols that would actually map to become a CT abdomen and pelvis. So as you see, there are multiple different protocols, whether they're adult, whether they're with contrast, whether they're called oncology, whether they're called enterography, but they're all CT abdomen and pelvis. So a knowledgeable tech has to take each of the different protocols that are done and lump them into some type of legitimate, meaningful map for ongoing comparisons. Next slide. Here are the reports that are generated, and we can see that there has been some change in the reports from 2011 to 2012. You'll notice that a median value has been added on the lower bar graph from 2012. This allows the site to actually look more discreetly compared to all DIR sites around the country. Also, a histogram is given. It's much more robust in 2012. We can see visually where our scans actually fall compared to all of the other dose index registry sites on the histogram above. And you can see our protocols here cluster significantly lower than the spread of all dose index registry sites, which I have to say I'm happy about. To be included in this report, in the adult report, patients have to be greater than 18. All the exams need to be tagged by that mapping tool. A minimum of 100 exams from 10 facilities need to be mapped to the same Radlex Playbook ID. And all the graph plots need to have at least 10,000 examinations behind them for the comparisons. Next slide. The reports come in two forms. They come as a PDF, which gives the dose indices per scan. It gives CTDI volatile, DLP, slice, and now size-specific dose estimates have also been given, and this was added in fourth quarter 2012. One thing to remember is that for each of these protocols, the single largest value is used from any aspect of the DICOM report, so a multi-phase study would be underestimated. You'll only have one value that could come from any one of 2 or 3 phases, so you would not be calculating the contribution from the other phases with lower values. The box plots, as I showed you, are based on a median value. The histograms that are given give a quick visual cue where the facility can see how their scans stack up against all of the other DIR sites. A second set of reports that you access from the website, the aggregate reports, are available as Excel sheets. I'll illustrate those to you in a second. These are extremely useful reports as well. Next slide. So here you can see just a couple of more reports from our site. Here's the size-specific dose estimate of an abdomen and pelvis from fourth quarter 2012. We're happy about where our median is. We're happy that our scans cluster. Our histogram has a mean value lower than the national average. So we are quite happy about the way we are practicing for abdominal pelvic CTs. Here's for kidney stone. Again, you can see that our doses, our median, are in the first quartile or actually lower than national and local practices. You can see the way our histograms stack up in terms of the dose indices used for our kidney stone protocols. Again, we are quite happy about the way these are looking. Now here's our CT brain. Here in the fourth quarter 2012, our median is higher. Our histogram of values is quite a bit higher than national average, and clearly this is something that we can focus on and look at going forward. Next slide. Now, to get the aggregate reports, you go to the website. There is a tool to access these aggregated reports, and Excel sheets can be downloaded in any of the categories that are shown on this slide. Next slide. What you get is a sort of complex spreadsheet, but it's nicely color-coded to show which scans are below the 25th percentile, which are between the 25th and 75th percentile for dose, and which are over the 75th percentile of dose. This gives you a very rapid way to kind of look at individual scans, pick them out, and focus on them for protocol modification. Next slide. One of the things that we wanted to do was to try to look at our individual scanners. This is actually quite difficult to do currently on the ACR. These are 4 different scanners at our facility, but still this degree of reporting is not quite where it needs to be, although it is being addressed. Next slide. As I said, this is difficult to generate for each individual scanner. To look at each individual scanner, this is currently needs to be done manually, and it's quite difficult. How do we use this data in our practice? We have a CT protocol committee that meets quarterly. I chair that committee, and it includes representatives from each of the sections in the department, a radiation physicist and a chief quality tech. This committee reports to the Departmental Quality Control Committee. We share this data at each meeting. We look at scans that are in the 75th percentile, and we ask the section chiefs to relook at those protocols, and we want to try, if possible, to get them into the 25th to at least the 25th to 75th percentile levels. Next. There are some caveats with this, using this data. Again, we need to know that the mapping needs to be accurate. If an incorrect study is mapped to an incorrect protocol, such as a CT brain perfusion is certainly not the same as a CT brain with contrast, you could see how this would elevate the levels in that report. It's important to know the phantom size, obviously, and at least as in our place, we would recommend that a medical physicist be part of any protocol modification. The benefits of this tool: it's been effective for dose quality improvement and optimization. We can easily identify outlier protocols and let the sections make final determinations to what they feel is acceptable. We have more context here than a bottom line driven dashboard approach, because we can see the activities of other facilities. The ability now to get size-specific dose estimate reports is excellent, as this is likely going to be the most meaningful dose index going forward. And also, this has marketing benefits. I mean, we're not ashamed to show patients who are interested in how we operate our CT scanners that they're lower than the guy up the block, the guy and the other people in the region, and we're doing quite well nationally. Next slide. I do have a wish list, which I've shared with the ACR. I wish there was some easier access to the aggregated reports, that they could be somehow put into the PDF. The ability to generate changes in the dose indices over time is something that's being worked on by the ACR. We want a yearly report that sums quarterly reports. And again, easier methods to look at individual scanners within the department. And as I said, many of these are being addressed for release in late 2003. There are some challenges using the dose index registry. There are inherent problems with the with the CTDI vol. Again, highly dependent on accurate mapping. We talked about the single value that's used. Although on the Excel sheets, you can see the value for each of the phases of a multi-phase study. And as I mentioned, it's difficult to look at individual scanners within the department. And just finally, the goal of this project is for optimized dose. It's not to drive down to some numeric value that yields non-diagnostic scans. This is something to help us fine-tune and be sure that we are operating, getting the highest quality diagnosis at the lowest possible dose. Thank you for your attention.